IGCSE 0625, June 2020, paper 41. And this is, we are going to be doing questions on electricity and magnetism only. So this is question number 7 of the paper. Okay, the first question says an electromagnet consists of, remember me being a teacher, you will find me that I underline important information. So an electromagnet consists of a solenoid X made of copper. Solenoid contains an iron core, right? An iron core. So it's important that you highlight the information along the way. You need to explain why structure of copper, structure of, okay, specifically they are talking about what? Structure of copper. Explain why structure of copper makes it suitable material for the wire. What's there in the wire? There's current in the wire, right? There's current in the wire. So what makes copper suitable for this? How this makes the copper suitable? So what copper is basically, copper has a lot of free electrons. Copper has a lot. In other terms, we say that copper has a sea of free electrons. A lot, or you can say has a sea of free electrons. Sea of free electrons. Free electrons. Making it a good conductor. Making it a good conductor. Mentioning the word good is important. Making it a good conductor of electric current. All right, so this is an important keyword. All right, that would score you 2 marks. Then the next question is, iron is suitable material for the core of an electromagnet. Copper is suitable material to be used as a wire. Why? Because it has a sea of free electrons. It has a lot of free electrons, and that makes it suitable. But for the core of an electromagnet, we use iron. So why it's suitable? Why it's suitable for that? Why it's suitable? Because iron is a soft magnetic material. It can easily be magnetized and demagnetized, right? So whenever I need the electromagnet to work, the iron should be magnetized, and when that's not in use, then there should be no magnetism left behind. So iron is a soft magnetic material. Iron is a soft magnetic material. One mark. Soft magnetic material. It can be easily magnetized and demagnetized. Magnetized and demagnetized. So it's suitable to be used as an iron core. All right. Then figure 7.1 shows electromagnet inside a solenoid. Describe and explain what happens in solenoid Y when solenoid X is connected to an alternating current power supply. So you need to describe and then explain what happens in solenoid Y. Which is solenoid Y? This one is solenoid Y, this outer one, right? This large coil. This is solenoid Y. This large one is solenoid Y. So what happens in solenoid Y when solenoid X is connected to alternating supply? Now remember that when there's an alternating power supply, that means there would be an alternating current. There would be alternating current, right? So when there's an alternating current, what happens? A current creates a magnetic field. A current creates a magnetic field. All right, so that means there would be an alternating magnetic field, and that alternating magnetic field in solenoid X will do what? Will cause a current in solenoid Y, an induced current, an induced EMF, in fact, right? Got it?
Yes, sir.
So, how will we phrase this? You will write that alternating supply or alternating current, alternating alternating current, alternating current causes alternating EMF. Oh, sorry, alternating magnetic field, magnetic field, magnetic field in solenoid, solenoid X, right? Which links, which links with solenoid, solenoid X, solenoid X. Or instead of link, you can write, use the word, you can use the word cuts, right? Cuts, which links with solenoid X, and hence induces, induces an EMF, induces, induces an EMF in solenoid Y. Got it?
Yes, sir.
Over here, by mistake, I think I would have read it out as X as well, but this is not X, this is Y, right? Field in solenoid X links with solenoid Y and hence induces an EMF in Y, right? A switch and a lamp are connected in series with the terminals of Y. When the switch is closed, the lamp lights up at normal brightness. Describe and explain what happens to the current in solenoid X when the switch is closed. What happens to the current in solenoid X when the switch is closed? So, can you guess what will happen or what have you written?
Sir, I missed part B.
Oh, you did not do part B?
No, sir, I missed it.
Why? Alright, anyhow, switch and lamp are connected in series with terminals of Y. When the switch is closed, the lamp will light up at normal brightness. What happens to current in solenoid X when switch is closed? So definitely when I close the switch, current in solenoid X will increase. Current in solenoid X will increase, right? Current in solenoid X will,
Increase.
right? To supply the power used in Y. To supply the power used in Y. So you will write that current in solenoid X will increase. So that power can be supplied to be used in Y. To supply power used in Y. Okay. Then write If you have missed it, then you should note down these answers. Then the power supply used, this is the second question, the same paper, June 20, paper 4-1, and this is question number 8. Okay, so the question says that the power supply used in an electric vehicle contains 990 rechargeable cells, each of the electromotive force 1.2 volts. 1.2 volts. Cells are contained in packs in which all the cells are in series with each other. The EMF of of each pack is 54. So every pack has how many cells? 54 cells. Number of packs in the power supply is to be calculated. Number of packs. So power supply is how much? 12 volts. Each pack is how much? 54. Each pack is how much? 54, right? And power supply contains 990 rechargeable cells. 990 rechargeable cells. You know that every pack has how many cells? Have they written that? Sorry, that is what we have to find, right? So the cells are contained in
Yes.
pack in which all the cells are in series. EMF of each pack. So if the EMF of each pack is 54, if the EMF of each pack is 54, and each cell has how much? 1.2 volts. Each cell has 1.2 volts. Now we know that in series the EMF add. So if it's 54, the total EMF of one pack, and one cell is 1.2 volts, I need to divide 54 by 1.2. 54 by 1.2. Why? Because this is the EMF of one pack. EMF of one pack. And then this is EMF of one cell. EMF of one cell, right? So what will I get with the help of this? I will get the number of packs, number of cells in each pack, number of cells in each pack, right? In each pack. So
Yes, sir.
please do this and let me know what is the answer. 54 divided by 1.2.
45.
45, right? So 45 cells in every pack. 45 cells in every pack, right? Now they are saying that the power supply used in electric vehicle contains 990. Power supply contains how many cells? 990 cells. And each pack has 45 cells. Each pack has 45 cells. So I need to find the total number of packs. So what will I do next? I'll just divide 990 number of cells divided by each pack. That is 45. Tell me what is the answer to this?
22.
22 packs. 22 packs. 22 packs. Right. Now, just let me quickly go through it again. They were asking the number of packs that are used in the power supply. Number of packs that are used in the power supply. They have already told me that the power supply has 990 cells. Has 990 cells, right? And I know that each cell is how much? 1.2 volts. Each cell is 1.2 volts. I also know the EMF of one pack, the EMF of one pack. So as I know the EMF of one pack, with the help of this 54 and the voltage of one cell, I'm able to find what? I'm able to find number of cells that are used in one pack. Number of cells that are used in one pack. 54 divided by 1.2 will give me number of cells in one pack. Now I know that each pack has 45 cells, and in total I have a 990 cells. 990 cells. So 990 divided by 45, because every unit is of 45 cells. Every pack is of 45 cells. When 990 is divided by 45, what I will get? I will get the number of packs that are needed for this power supply. So a power supply with 990 cells. Each cell has 1.2 volts. I need to find how many packs are needed. It's 22 packs. All right.
Yes, sir.
When in use, each pack supplies a current of 3.5 amperes. Calculate the rate at which each cell is transferring chemical energy to electrical energy. So you need to find the rate. Whenever I use the word rate, you need to recall that rate is what? Rate is power. Rate is power. Hmm? Okay? Rate is power. So rate of energy. Power is rate of energy. Okay. So they are saying calculate the rate at which energy cell is transferring chemical energy to electrical energy. I know the current. When in use, each pack supplies how much current? 3.5 amperes current. How much current? 3.5 amperes current. And each pack is of how many volts? 54 volts. So power is what? Current into voltage. So I'll say 3.5 is the current into voltage, which is 54. I would want you to quickly use the calculator and tell me the answer. Quick, quick. And if I do my calculation, it should be.
189.
You have multiplied them,
Yes.
and what is the answer that you get?
189.
Okay, 3.5 and 54. 189. Let me see. Is there any problem?
Sir, why are you multiplying them by 54?
54 is basically what? The
Shouldn't you
EMF of
multiply them by the EMF of one cell, which is 1.2?
what? Calculate the rate at which. Okay, it's each cell. My bad. It's each cell transferring chemical energy. Yeah. So each cell is how much? 1.2. Good. 1.2. All right. 1.2.
Yes.
So what's the answer to that?
4.2
4.2 and unit
watts.
watts. So see, you need to read the question carefully. You just saw an example. I did not read the question carefully, and I missed this each cell. All right. Then the packs are connected in parallel to supply a large current to drive the electric vehicle. Why it's necessary to use thick wires to carry this current? So thicker wires have smaller resistance because we need larger current, so we need to reduce the resistance. Thicker wires have smaller resistance. So that means if I use a thicker wire, then less thermal energy, less electrical energy would be converted into thermal energy because of lesser resistance. And that would make the battery more efficient. Is it?
Sorry, sir, can you repeat?
Since I need larger current, so larger current means I would have to reduce resistance somewhere or the other. To reduce the resistance, one way is to use a thicker wire. Thicker wire means larger cross-sectional area, less resistance, more current, right? Less
Yes,
electrical
sir.
energy is converted as heat energy. So that makes the supply, the battery more efficient, isn't it?
Yes, sir.
All right. So I'll just write this down. Thicker wires have smaller resistance, right? For larger current, for larger current, thicker wires thicker wires are suitable because they have low resistance, low resistance. Okay, one mark. Because they have low resistance. So what would happen? Less less thermal energy less thermal energy is produced, right? Less thermal energy is produced, and that means it makes the battery more efficient, making the battery making the battery more efficient, right? More efficient. Okay, so then
Yes, sir.
there's this next question, and this is June 20, paper 42. June 2020, paper 42, and this is question 7. In my worksheet, it's number 4, but in actual paper, it's question number 7. Okay, so the question is saying that a student makes a transformer that uses an alternating current supply with an electromotive force of 12 volts to induce an output potential difference of 2.0 volts. The student is provided with two lengths of insulated wire and U-shaped piece of iron shown. Complete and label 7.1 to show the transformer connected to the supply and the output from the generator. You need to complete and label figure 7.1 to show what transformer connected to the supply and the output from the transformer. So what have you drawn? Let me check that. Okay. Okay. So where's your response gone? Zen. Yes. Okay. So you have made it or not? I cannot see. Yeah, it is. It is here. It is here. All right. So this is an iron core. Okay, perfectly. You have made the turns. Okay. So you had to mention what? You had to mention that the input and output, right? So one way is that you make the coils like this, just as you have made, and it's okay. What type of transformer is this? 12 volts, and induces an output potential difference of 2 volts. All right. So that means output is 2 volts. There's a little mistake in this diagram, and that is the number of turns in the output coil should be lesser. The number of turns in the output coil should be lesser. Why? Because the
Why
output is 2
less?
volts and the input is 12, isn't it?
Yes, sir.
So this is the supply. And is this supply alternating? Yes, it is. How do you represent alternating supply? Just with a wave like this between two dots, and you can just connect a load over here. All right, load. So that's how you do this. Explain the function of the piece of iron in the transformer. So why is this iron used in transformer? It should be used to do what? Link magnetic fields from primary coil to the secondary coil. Hmm? Make the field strength stronger in the secondary coil. Induce EMF better. Hmm? So iron core is used to link magnetic field from from primary coil to secondary coil. This would score you 1 mark, right? Secondary coil. And then the next point that you should mention is it makes magnetic field stronger. It makes magnetic field stronger. And this would score you 2 mark. And you could have also mentioned that it makes the electromagnetic induction better. It makes electromagnetic induction better. The examiner tip here is that don't worry if your line exceeds. You can write an extra line here. Okay, so the output of the transformer is connected to a lamp. Current in the lamp is 100 milliamperes. Transformer is 100% efficient. Calculate the input current to the transformer. So milli, whenever it's milli, 100 milli means 100 divided by 1000. So it makes it 0.1 amperes. Number one. Number two, calculate the input current. So I know that IP upon IS is equals to Vs upon Vp. What I need to do, I need to calculate the input current. It's 100% efficient, so whatever the power is in, the same would be the power out. I know the input and output voltage, and I know the current in the lamp. So the current in the lamp, it's a lamp. This load is basically a lamp, right? This is a lamp. So I know the current in the lamp, so this is output current, right? This is current in the secondary coil. Current in the secondary coil. So I can easily find IP, current in the primary coil. IP is equals to Vs upon Vp into what? Into Is. What are the values of Vs and Vp? Vs is 2 volts. Vs is how much? Vs is 2 volts. Vs is 2 volts. And Vp is how much? Vp is Vs, and this is Vp. This is Vp, right? Okay. 2 upon 12. 2 upon 12. 2 upon 12. 2 upon 12. Into Is. Is 0.1. So please can you calculate this and tell me the answer?
0.017.
Perfect. 0.017 amperes. Another transformer is used in a school laboratory to step down a mains supply with PD of 110 to 12 volts. Transformer is mounted in a metal case. State and explain an essential safety feature required for this arrangement. So metal cases are always required to be earthed. Why? Metal cases, metal case should be earthed. Should be earthed. Why? In case the wire falls and touches the case, so that if the if the wire falls and touches the case, touches the case, it becomes less harmful. It becomes less harmful. Right?
Yes,
Okay.
sir.
All right. LED is a diode that emits light when there's a current in it. Draw a circuit diagram showing LED connected so that it is lit in series with a battery and fixed resistor. So 4 marks. LED is a diode, you need an LED. It's connected in series and fixed resistor. So this is a fixed resistor. To this, there's an LED connected, which is a light emitting diode, which is a light emitting diode. Normally, LED is made like this. Light emitting diode, right? And that's connected with a battery. That's connected with a battery. So let's say this is the positive end of the battery. Or you can make, sorry, LED is light emitting diode, so diode should be made just like this. My bad. Diode should be just made like this. Okay.
Yes, sir.
So this is the positive end. This is the this is the positive end, and this other one is the negative end. Negative end, right? So the positive end of the battery should be connected to the positive end of the diode, and this should continue just like this. Have you made this diagram?
Yes, sir.
Okay, that's fine. Right, perfectly okay. Then you need to calculate resistance. Resistance is voltage upon current. Voltage is 3.1 when it's lit, and current is 0.03 amperes. So what's the resistance? What is the resistance? Yes, Zen.
Sir, 103.
100 ohms, right?
Yes.
Okay. 8.1 shows power supply of EMF 10.5 volts in series with lamp and heater. PD across lamp is 2.1 and current in lamp is 1.5. Resistance of the heater. So this is 10.5, the supply, right? Lamp is getting how much? 2.1 volts. So what is the voltage across this heater? Quick. Hmm?
Sorry, sir.
What is the voltage across heater? What is the voltage across heater?
Uh,
Sorry?
10.5 minus 2.1, so 8.4.
Yes.
8.4, sir.
Right. And the current in the lamp is 1.5 amperes. So here also it's 1.5 amperes, right? So resistance is again voltage upon current. Okay. So what's the value?
5.6 ohms.
Yes.